I've got a few announcements. The first one is the assignment detail. It says the 8th of August in there, which I've just realised. That's not correct. I will make a separate announcement about the assignments. I'll give you example ones. You'll have at least one tutorial to do it. There's been a variety of reasons for that announcement being incorrect, but it will be later than that. So today, what I'm going to do is download and install R. I realise I've forgotten to show you how to do that. I'm going to spend most of the mathematical content talking about the factorial function and Stirlings approximation and how that's used in mathematics and how it's used in statistics. And if I've got time, I'm going to go through a little bit of the Gaussian distribution, but in somewhat more detail than I have done in 715. So right now I'm going to show you how to download and install R. You must do this. You will have a final exam which is 50% of the course credit where you will be expected to use R yourselves with no help. And if you're familiar with R, everything will work nicely. And if you're not, it's going to be a very difficult procedure. To download R, just do what I do. Search for CRAN, Comprehensive R Archive Network. Search for it. Now you can just go straight to R for Windows, but let's just go to the CRAN website. This is the R website, or one of the R websites. It's not the home page. And you can see R for Linux, R for Mac. Any Mac users here use this one. Download R for Windows. So let's have a look at that. Binaries for the base distribution. So it's just the first click there. Download R311 for Windows. So it should take a little bit of time to work. It'll take a little bit of time. How many time? 3 minutes remaining. It's quite a large package there. So look, it's done 5 megabytes out of 54 already. So I may as well get on with something else while that's happening, and then I'll install it. We've been talking quite a lot about the binomial distribution. And that's going to be the starting point for quite a lot of the content of this course. The binomial distribution is the simplest and easiest one, but it's one of a family of distributions. So I'm just going to give you a slightly different form for it. Size n and probability of success equals p. Probability of R successors equals n, choose R, n minus R, which we covered before, p to the R, 1 minus p to the n minus R, which you've seen before. I'm just going to rephrase it in a slightly different way. I'm going to talk about A plus B trials instead of n, A successes and B failures. So you can see the total number of trials is A plus B, which matches the total number of trials there. And with this formulation, it's A plus B, choose A, B. It's always a little bit difficult to write this one because I've got two separate, it's not a product of A and B, it's two separate letters there. P to the power A, 1 minus P to the power B. And I can further simplify it by writing P equals the probability of success, prob of success. And I'll say that Q equals 1 minus P equals the probability of failure. So the binomial distribution with this notation is simply the probability of having A and B, successes and failures, equals A plus B, choose A, B, P to the power A, Q to the power B. Simply because this 1 minus P turns into a Q here. How are we doing with our downloading? Oh, it's finished. And I can rewrite that as A plus B factorial over A factorial, B factorial, P to the A, Q to the power B. A much more symmetric way of writing. I want to encourage you to try and think like that when you see an expression like this, you see how there's an asymmetry between successes and failures, and really failures and successes, they're just alternative words for the same process. This is a much more symmetrical way, but still, because we've got symmetry between A and B, but still we've got an asymmetry between success and failure. And here we don't, because we've just got P and Q. Oh, with the specification, of course, that P plus Q equals 1. It's a much more pleasing way of handling it. And I'll return to this formulation later when we come to the Dirichlet and multinomial distributions. Let's see how R is getting on. Oh, there it is. Can I just execute that? Select the language. English, yeah. Install wizard. Next. Yeah. Yeah. Just say yes to all the defaults. You're not going to come to any harm by doing that. So it just downloads itself. And finish. And that should be done. There we go. And it's put its... there are two icons. There's RI386 there and a 64-bit. And I don't really understand the difference between them. I don't really know what that means. So here we go. Just make that a bit bigger. While I'm talking about R, if we go back to the CRAN page, we can click on packages here. What's going on? Oh, it's still loading there. Here we go. And sorted by name here. And you'll see as I'm scrolling, you can see the scroll bar on the right-hand side. Each line here corresponds to a package, which is a self-contained piece of R coding. So it's the case that just about any statistical technique you've ever heard of, and in fact lots of statistical techniques you won't have heard of, somebody somewhere will have coded it all up. And there's quite a lot of my research involves writing. Here we go. Here's one of mine, Aylmer, which is mine. So quite a lot of my research involves taking R forwards and writing new functionality for R, which is a computing embodiment of new statistical theory. So that's me, and that's my colleague Luke West. And I wrote this distribution, one of a few packages which I've written, and I've made it available. So if I can download R in 2 seconds flat, you can too. And I want you all to do this, and I want you to do it at home. I want you to be able to use R in your sleep, basically. Okay, so let's just put that down there. One disadvantage of this binomial distribution here is that it's got this factorial function in it. And I did cover the factorial function, but I'll just remind you what it is, function. N factorial equals 1 times 2 times 3 times n. So for example, 10 factorial equals 1 times 2 times 3 times all the way up to 10, which equals, well, of course, I'll get R to do the hard work for me. Factorial 10, which comes out to be, is that 3 million? Yeah, 3.6 million. And of course, the first thing that should come into your head is this. Can I verify that? Am I doing what I think I'm doing? Can I check it? Can I evaluate that sum in some other way? And of course I can. I can just write it out. 1 times 2 times 3 times 4 times 5 times 7 times 8 times 9 times 10. And so they agree. However, this is quite an unwieldy and difficult process. Calculating factorials is hard because you've got quite a lot of multiplication to do here, and the factorial function is not easy to deal with in the same way that logarithms and exponential functions and polynomials are easy. Factorial function is quite spiky and difficult, very computationally intensive, and quite hard to evaluate. So what I'm going to do is I'm going to introduce an approximation to the approximation to the factorial function, which allows us to evaluate an approximate value for the binomial distribution, and we'll see some advantages accruing from this. And it is called Stirlings approximation. Let me do that again. Stirlings approximation. Sometimes you'll see Stirling series, and I'll cover the first two or possibly three members of the series. And I'll just state out what it is. N factorial, and here's a new symbol for you, is approximately equal to. And I can't explain precisely what that means because it's quite a technical mathematical thing, but what it really means is that the left-hand side is a good approximation to the right-hand side, in a sense which I could make mathematical, but it would take us far afield from the course. Root 2 pi n. You happy with pi? You happy with e to the power? N to the power n. And that's it. It's a good approximation. I'm going to put that in quotes because I'm not defining exactly what good means. It would take us far afield to cover all the limits and the analysis that we need. It's a good approximation. If n is large. And again, that's in scare quotes because I'm not really defining what large is. You will have to know Stirling's approximation, and you will have to reproduce it in your final exam. You will have to know that, and there's no argument about it. So let's just evaluate that. There's factorial 10, which I calculated with R. Let's work out what Stirling's approximation is. All I've done is basically write down the approximation root 2 pi n e to the minus n to the power n. I've just expressed it in our format. But there's quite a lot going on here. I dare say I'll make it look easy, but you need to know that these, for example, are round brackets, not square brackets. You need to know that the e to the power n is written exp for the exponential function. And this little caret here is a power. Root 2 pi n, e to the minus n, n to the n. Let's see how well it's done. N's not found, of course it isn't. I want people to go through this. I've got to say this again and again and again. I want people to have their experiences of having errors and screw-ups in this kind of context here where it doesn't matter and you can patch it up. I've seen people panicking in exams because this kind of error happens, and they're not prepared to deal with it because they haven't put the time in making the screw-ups in their own time. And of course, all I've done is write down this formula here, but I've not told it what n is. Why don't I tell it what n is? N becomes 10. And now if I evaluate this line, now I've told it what n is, it'll think, oh, I know what n is. It'll plug n equals 10 into this formula here. Let's have a look at it. Not bad. 362, 359. So it's correct to about 1%. And in fact, if I want to work out the percentage error, I will divide by factorial 10. Oops. 0.99. So it's correct to within 1% error, which isn't bad. Think how complicated that factorial function is. All this multiplication, all this stuff here. And this is a very, very much simpler formula. And as we'll see later, it's very much more conducive to working out properties of the binomial distribution. Just as an observation here, n has now changed. Now it's 100. Remember I said that the approximation was good if n is large, and the approximation gets better as n gets larger. So here's factorial 100, 9.332 times 10 to the power 157, an astronomical number. Let's work out let's work out Stirling's approximation here. And you see how more accurate it's getting, 9.32. So it's correct to within 0.3 of 1%. As n gets larger, the approximation gets better. Okay.
Sorry, I see the factorials here. It ends with $sign. Is it extended?
This?
Yes.
Oh, that's just because it's gone off the end of the screen.
Yeah.
If I do that, you see it's just appeared. The dollar just means, oh, you've cut it off. Just be aware that there's... Well, you could tell anyway because it had opened that bracket but not closed it. All right, so there's Stirling's approximation. It's an interesting story how this came up, how this was discovered. It's actually elementary, although it's elementary but complicated. And besides, this course is a practical course. It's not a course in mathematical analysis, so I could prove it, but it would take the whole course and we'd do nothing else. It's a bit of a waste of time. All right, so how do we use it? Well, what I'm going to do is start out with a binomial distribution of size 2n. So it's even. Because I'm taking a multiple of 2. And I want to figure out, and I want the probability... just a second, I'm getting out of sequence here. And the probability of success, p equals 1/2. So it's a fair coin. And we're going to toss that coin an even number of times. And I want the probability of having n successes and n failures. An even split. Okay? Well, we can work that out with, we can give an exact answer to that. I can give you an exact answer. But something quite remarkable happens when you apply Stirling's approximation. Am I okay writing with red? Is red visible? Okay. Well, it's 2n, choose n. 1/2 to the power n, 1/2 to the power n. That's the answer. And I can even expand the choose function here. So it's 2n factorial over n factorial squared times 1/2 to the power 2n. Which is a poor answer. It's correct. But it's a poor answer in two senses. The first sense, it's a poor answer in two senses. The first sense in which it's a poor answer is that it's difficult to evaluate. I can hear my mathematical colleagues howling in outrage that that is not a good reason to call it a bad answer. But in a practical course, we've got to evaluate stuff. And if this is hard to evaluate, I mean, if I put n equals large, a large value, you've got to do lots of multiplications. It's also difficult to understand. It's difficult to understand. It's not immediately obvious what's going to happen as n increases. As n gets larger, does this probability increase or decrease? It's not obvious. And those are deficiencies of that answer. They wouldn't cut much mustard with a mathematician who would say, well, that's the right answer, deal with it. But in a practical context, if you don't understand it, then that's hard. That's a problem. Okay. So what I'm going to do, of course, is to replace these factorials with Stirling's approximation. Well, actually, let's start out with the easy. Start out with the easy one. I'll switch over to black actually because that blue one is not the best. N factorial is root 2 pi n e to the minus n, n to the power n. Therefore, 2n factorial is approximately root 2 pi 2n, e to the minus 2n, 2n to the power 2n. All I've done is taken what was n here, I've just written 2n for there. A lot of people start gasping in horror when I do this. All I've done is written 2n there. Okay? And n factorial is approximately, oh, I've got it here, haven't I? I've got n factorial. N factorial squared, why am I doing that? It's because I need it from down here. Is approximately equal to, well, I'll do it in stages. Root 2 pi n, e to the minus n, n to the n, all squared. I'm assuming you understand how powers work. I happen to know that it's part of the NCEA syllabus. If you don't understand how powers work, you've got a problem. And I will put up screencasts about powers and how powers work and how to raise powers to powers, that sort of thing, on AUT Online. Would people value that, reminding of how powers work?
Sure.
How many people understand this and how many are struggling? You're struggling? How many people? How many? Struggling. How many people are not struggling? It's equally split. Maybe I'll go through it a little bit.